All right, so the first thing that we need to talk about with regard to these, and this is true for cyclohexane as well as any ring structure, is this concept of a stereoisomer. We talked about a different type of isomer last class called a constitutional isomer. All right, for rings in particular, they can also have what are called stereoisomers. This is when you have the same molecular formula, the same connectivity of atoms, all right, but they differ in their spatial arrangement of those atoms. Okay, these are something that are going to be unique to rings. Okay, so these aren't going to be true for alkanes all by themselves. Alkanes do not have any stereoisomers, but cyclic alkanes can have stereoisomers. We'll also see when we talk about alkenes, they may also have stereoisomers. All right, but we haven't even gotten there yet. So for right now, these are unique to our cyclic alkanes. So what do I mean by that? Well, so first of all, let's just note, if I don't have a ring, let's say in this molecule right here, these two chlorines are starting out on opposite sides of my molecule, right? One's going to be on a wedge pointing out towards you guys. The other one is on a dash pointing towards me, right? But in these alkanes, we can rotate about all these single bonds. So I can just rotate this, and now all of a sudden my two chlorines are pointed in the same direction, right? We can rotate about single bonds, so these guys can move to the same side. As soon as we lock these things up in a ring, this ring is preventing the rotation of these single bonds. They can jiggle about a little bit, but they can't do a full 180 rotation because they are locked in that ring. So let's say that I have two chlorines, and I put them on the same side of my ring, right? They're both pointed, in this case, down at the ground. They're on the same side of that ring, the same face. There is no way for me to rotate this to make it so that they're pointed in opposite directions. Okay, likewise, while I'm going to steal your model, if I started out by putting them on opposite sides of that ring, such that one is pointing up and one is pointing down, they're going to be stuck like that. I can't rotate this to have them all on the same side. So these are very, very similar molecules. They are both cyclohexanes. They both have two chlorines. Those chlorines are located 1, 2 carbons apart in both of these molecules. Nonetheless, these are distinct molecules. I can't rotate this to be like this one. Okay? So these are what are called stereoisomers. So an example of a pair of stereoisomers. This is going to now be utilizing those dashed and wedged bonds that we talked about before. All right, so if one has, let's use methyl groups because we know how to name those. One has these two wedges. The other one has one wedged bond, but one dashed bond. Okay, this would be a pair of stereoisomers. All right, let's just focus on one here. Everybody take a second and name that left molecule for me. right, so remember, what's my parent chain here? The ring, right? Anytime you got a ring in there, that's your parent chain. So my parent chain here would be a cyclohexane. I have this one carbon substituent and this one carbon substituent. So this is a methyl group. This is a methyl group. Remember, if there was only one of them, I could leave off that locant, but anytime there's more than one of them, I am going to have to put those numbers in, right? In this case, wouldn't matter which one I start from. They are located 2 carbons apart. So this would be 1,2 dimethyl cyclohexane. All right, but this other molecule over here, this is also a 1,2 dimethyl cyclohexane. But we just established that these are not the same molecules. These are stereoisomers of one another. They're very similar. They will have very similar chemical properties, but they will not be exact. They will not be identical. They might differ by just a few, 1, maybe even 0.5 degrees Celsius in terms of their boiling point, but they're not going to be the exact same. They are not the exact same molecules. So, because the whole point of nomenclature is to uniquely describe a molecule, we have to include something out front of the name that indicates the stereochemistry. Okay? So this one on the left, this would be what we call the cis isomer, and the one on the right would be what we call the trans isomer. Okay, this cis and trans designation, that is the stereochemistry of our molecule. All right, again, we established we got 2 separate molecules here, and we got to uniquely identify them in our name. So if we're trying to uniquely identify them, we have to include this stereochemistry. Okay? That term cis means that those 2 bonds are pointed on the same side. And that stereochemistry trans means that they are on opposite sides. Okay, so again, unique to rings, we have this concept of stereochemistry here because the structure of our rings prevents the free rotation about our single bonds. So if we have 2 methyl groups that are both pointed up away from the ring, they're stuck. They're stuck on that side of the ring. So we got a special name for those. Those are the cis stereoisomers. If those 2 methyl groups are pointed on opposite sides of the ring, they're going to be stuck on opposite sides of the ring. We call those the trans isomers. Okay? So something very specific to rings. Again, normal alkanes don't have this. But with our rings, we have this stereochemistry that we have to consider. Okay? And these would be part of the name. You would build them into your name, cis dash, the normal name of the molecule, or trans dash, the normal name of the molecule. All right, so then just to finish this up here, take a second and name these 2 for me. There's two carbons. This is how you would do an ethyl group. You always show the stereochemistry of the thing connected to the ring, and if it's any longer, they're just normal straight line bonds. All right, so step one, I'm just going to name them like I normally do. My parent chain is the cyclobutane. I have these two methyl groups on there. This is a methyl group. This is a methyl group. All right, they're both identical, so it doesn't really matter which one I start at. But importantly, they're located 3 carbons apart, or on carbon 1 and carbon 3. So without my stereochemistry, this would be 1,3-dimethyl cyclobutane. All right, but I got these dashes and wedges, so I have to specify my stereochemistry. Are they pointed on the same side or opposite sides? Opposite sides, so this would be the trans 1,3-dimethyl cyclobutane. All right, my next one, same idea. I'm going to find my parent chain, my 5-carbon ring, cyclopentane. All right. This would be a 1-carbon methyl group. All right, and my other substituent, if we just want to look closely here, this is how you would represent an ethyl group with stereochemistry here. I have 2 carbons in this substituent. Typically the one that's on the ring, you show which direction it's pointed, and every bond after that is just a normal straight line. So if I wanted to make this even longer, it would just be a whole bunch of zigzaggy lines coming off of it, right? So only that first bond shows you your stereochemistry. We'll leave it as an ethyl group here. When I got my ring, remember, I'm going to start at each one of my substituents. So my methyl group could be carbon 1, and my ethyl group carbon 3, or I could go the other way, right? And in this case, blue is a 1 and a 3. Red is a 1 and a 3. So which one am I going to go with, red or blue? Why the red? Because I got a tie, right? So I got to go to that tiebreaker, which is alphabetical order. So indeed, my red numbering scheme is what I want. So 1 ethyl, 3 methyl, cyclopentane. All right, but again, I can specify the stereochemistry of this molecule. Are they pointed on the same side or opposite sides? This would be the same side. They're both wedges, so this would be the cis isomer. Okay, and to be clear, they could both be wedges, or if I switched these so that they were both dashes, this is also a cis isomer here. All right, pointed in the same direction. All right, cool. So let's go back to our cyclohexane models. Now we're going to spend some time specifically talking about the conformations of cyclohexane. All right, we said that cyclohexane is the most stable of all of our ring structures. Okay? Now, it adopts a very specific configuration, which is what's called a chair structure. Okay? So I want everybody to take a second and to kink their ring into a chair structure. Let me show you what I mean. This is our cyclohexane, right? All of our carbons do not sit in one flat plane. We have 3 of them that are sitting above the plane and 3 below. Notice how every other carbon here has 1 hydrogen pointed directly up, right? This carbon right here, for example, has its hydrogen pointed directly up. Skip a carbon. This one also has its hydrogen pointed directly up. Skip a carbon, the back one, right? So every other carbon has a hydrogen pointed directly up. The other ones have their hydrogens pointed directly down. Okay, yep, awesome. Yep. Every other, yeah, so this one up, that one up, that one down. You can grab them all, kids, right up the front. Yeah, you're right there, Emily. One more. This one, and then this one. These 3 pointed up, these 3 pointed down. Okay, cool. So we're going to need to learn how to draw these chair conformations. Okay? So what we're going to do is we're going to sort of look at it from the side here. You see how it makes this little, I don't know why they call it that. I guess it is kind of like a chair. They're pushing it a little bit. But nonetheless, they call it a chair conformation here, where this little zigzag. All right? So how do we draw our chair structures? First thing you're going to do is draw 2 parallel lines slanted downward. Okay? But that bottom one has to stick out a little bit further than the top one. So here's step 1, these 2 parallel lines. All right, step 2. On the left-hand side, I'm going to draw a triangle. I'm going to connect these 2 lines with a triangle that's pointed up. It's like this and like this. All right, and step 3, I'm going to do the same thing on the other side. But now I'm going to draw them connected by a triangle that's pointed down. Okay. So let's all check our structures real quick. If we have a proper chair structure, it should have this zigzag to it, right? So this is pointed up. Whoops, this is pointed up and then back down again and then up and then back down again and then up and then back down again, right? So I have this zigzag structure. A common error that people make when they draw these chair structures is if you accidentally made your first two parallel lines staggered the wrong way, you would get something like this. Okay, and I can tell this is wrong because it goes up, 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 down, down, down. All right, so we need that zigzag to our chair structure, just like we see if we take our cyclohexane model and we hold it to the side here. Okay, so this one's bad. This is what we want. All right, so for the sake of practice, let's draw a big one down a little bit further, and we're going to annotate this. So we'll get a nice big chair structure. Again, I'm going to draw my two parallel lines. The bottom one is going to extend a little bit further. I'm going to connect these with a triangle going up, and on the other side with a triangle going down. All right, and everybody take your structure that you have in front of you, sort of turn it to the side and make sure that you can see that there are 3 carbons that are kind of sitting above the plane of the ring. If I were to make a plane through this ring, I got 3 carbons that are slightly above it. Those are the ones whose bonds are pointing straight up, right? Every other carbon has a bond pointing straight up, right? And then every other carbon has a bond pointing straight down. Those are the carbons that are slightly below the plane of my ring. All right, so we're going to draw in these bonds on our structure here. On our chair structure, we have 3 carbons sitting at a point, sitting at the tip of a triangle here, right? These 3. Take a second and convince yourselves that you can see in our chair structure that these are at the point of a triangle, the top of a triangle, a peak, let's call it. Okay? Those are our 3 that have these bonds sticking straight up. So if I'm going to draw my hydrogens on there, I'm going to draw these bonds pointed straight up from those 3 carbons. So these carbons located at peaks have bonds pointed straight up. All right, the other 3 carbons are sitting at a valley. They're sitting at the bottom of an upside down triangle, right? These 3, 1, 2, 3. Okay, these are the 3 in our chair structure that are sitting slightly below the plane of that ring, and they have their bonds pointed straight down. So if I'm going to draw those bonds, these are pointed straight down. Okay, so just like in my model here, every other carbon is sitting slightly above the plane of the ring, and they have their hydrogens pointed straight up. Every other carbon is below the plane of the ring, and they have their bonds pointed straight down. Okay? These positions, these straight up and down positions, are what we call the axial positions on our cyclohexane. Okay, so we have 3 axial positions straight up and 3 axial positions straight down. All right, now we only drew 1 hydrogen on each carbon, so we're not quite done yet. Notice that the other ones, if we ignore the ones pointed straight up and straight down, all those other bonds are pointed sort of away from that ring. Right? If I hold it like this, I can see that each carbon has a hydrogen on it sticking away from that ring. Okay? And they are pointed, slightly different directions, but they're basically all just pointed away from the ring. So I'm going to draw those in. So all carbons have bonds pointed away from the ring. We call these the equatorial positions. So every carbon has 2 bonds, one of which is pointed straight up or down. That's what we call the axial positions. And the other bonds are pointed away from the ring. That is what we call the equatorial positions. All right. Now I'm going to take my structure, my ring structure here, and I'm going to replace all my axial positions with green marbles so we can watch them. All right, so let's just all look up here. I replaced all of my axial all my axial bonds. I put a green marble on there so we can keep track of them, right? So we see how they're all pointed either up or down in this model, right? Okay, so molecules, they're never just standing still, right? They're constantly moving and shaking, everything like that, all right? We talked about how this structure is restricted. It can't freely rotate. Nonetheless, it undergoes what's called a ring flip. Okay, so I'm going to do a ring flip on this structure here, and let's pay attention to what happens to these green marbles. All right. What just happened? Where did they go? To the equatorial, right? From the axial position to the equatorial. All those green marbles that used to be in the axial position, I underwent this ring flip, and they all moved to the equatorial position. Okay, so these are these conformational changes that cyclohexane undergoes. It's constantly going back and forth, flipping back and forth from one chair to the other. All right, so we need to be able to represent that with our little chair structures that we learn how to draw here. All right, so we got this one here where we labeled our axial and our equatorial. Let's make a new one. Okay, everybody just take a second. We're gonna do two side by side, so save yourself a little room. But see if you can't do a chair structure from scratch here on one half of your page. All right, so I'm going to draw my two parallel lines. The bottom one's going to stick out a little further. I'm going to meet them at a point. I'm going to do the same thing on the bottom, but in the opposite direction. All right, let's put in all of our axial positions. Take a second and put in your axial positions on your chair structure. Remember, the peaks will have their axial position pointed up, whereas the valley carbons will have their axial position pointed down. Okay, on all of my axial positions, I want to keep track of what's what here. So on all these axial bonds, I'm going to put a blue square. You can both color code and symbol code, that's great. If not, just use the squares. All right, but we want to keep track of these bonds. All right, and then take a second and draw in your equatorial bonds. And we're going to label them with a red circle. So in this structure, my blue squares are all axial. My red circles are all equatorial. Okay, but as we said, this conformation right here, it's constantly flipping back and forth. All right, so now we got to draw the flipped chair here. And we're going to do it the same way, but when we start our first two parallel lines, they have to be pointed in the opposite direction of when we started on the left, right? So look, everybody look up here for a second. The first two lines that I drew were these two parallel lines pointed down to the left. I'm going to do the same thing, but I'm going to draw my two parallel lines pointed down and to the right. All right, now, keeping track of which carbon is which is kind of difficult with our chair structures, right? When this flip happened, we got to make sure we can tell which carbons on the left correspond to which carbons on the right. So let's label this rightmost or this leftmost carbon that's pointed up, carbon 1. All right, and then we're just going to go counterclockwise here. It actually wouldn't matter which direction that you went. Okay, all we're doing is numbering to keep track of who's who. So if carbon 1 is pointed up in my first chair conformation, once it undergoes the flip, it's going to be pointed down. So this is carbon 1 in my flipped structure. All right, everything that used to be at a peak is now at a valley and vice versa. So if I just go around, boom. All right, now just like before, all of the carbons at a valley are going to have their axial positions pointed straight down. And everything at a peak has its axial position pointed straight up. All right, and then if I draw in my equatorial positions, again, they're pointed away. All right, and if we look closely at carbon 1, I saw that this square was my top bond, and the circle was the bottom bond. All right, so if I go to carbon 1, it's got to be the same here. My square is going to go on top of my circle, All right, but on the left, was that square in the axial or equatorial position? On the left, it's on the axial position. What about on the right? It's on the equatorial position. So again, we saw that with our model here, the flip where your axial positions become your equatorial positions. That's what we want to make sure to keep track of here. It's going to be the same thing for all of these carbons. Right? For carbon 2, the red circle was on top and the blue square was on the bottom. On the left, the blue square was in the axial and now it's in the equatorial. All right, so for our chair flip, we see our axial becomes equatorial. And our equatorial positions become the axial positions. That's what happens in our chair flip. So if we have a ring of cyclohexane, it's constantly just jumping back and forth between these two conformations. Okay, for cyclohexane, specifically, they're all just hydrogens, right? All of these bonds are just hydrogens. So these two chair conformations are going to be like energetically equivalent. It's not like one's better than the other. So it's constantly jumping back and forth between the two, but it spends about 50% of its time in one structure and 50% of the time in the other structure. Not one of them is more favored than the other. They're all just carbon-hydrogen bonds in the axial and equatorial position. All right, but that is not true as soon as we start adding substituents to their ring. It's going to turn out that one of these chair conformations is going to be more preferable than the other. All right, so let's take a look at that. Cool, so now we're going to look, instead of just looking at regular old cyclohexane, we're going to go ahead and throw a methyl group on one of those carbons. All right, so we need to be able to take this structure right here and draw the chair diagram, the chair model of that structure. Okay, so everybody take a second. Let's draw our chair. All right, let's call this carbon 1. All right, we have two bonds on carbon 1. Which direction should the axial bond be pointing, up or down on my carbon 1? Up, right? It's sitting at a peak, right? At the, the top of a triangle, not the bottom. So it's going to have its axial position pointed up and its equatorial position to the side. All right, since my methyl group is on a wedge, it's pointed up at me, right? I'm going to draw that methyl group on this top carbon here, our top bond here, right? That's my methyl group pointed up out of the page. Okay, so now everybody take a second and draw me the flip of this structure. How are you going to draw the flipped chair structure of this molecule?
Does it always have to be that number one? Or does
You can do it arbitrarily, yeah, but I mean it's helpful to be consistent. But no, you'd be able to get to the same answer regardless of what you picked. The real thing is you have to make sure your carbon 1 on the left is the same as carbon 1 on the right. That's kind of the hard part. All right, so if you want to look up here to watch me draw the flipped structure, again, on the left-hand side, I had started with these parallel lines pointed down and to the left. So on the right-hand side, I'm going to start with these parallel lines pointed down and to the right. Add my triangles. Okay, remember if carbon 1 is pointed up on the left-hand side, it's got to be pointed down on the right-hand side. So that's this one right here. Okay. Is my carbon 1 on the right going to have its axial position pointed up or down? This carbon right here, axial position, pointed up or down? Down, right? It's at the P, or at the valley, at the bottom, an upside down triangle, however you want to say that. So here are my two bonds. Okay. And which one is that methyl group going to go on, the axial or the equatorial? The equatorial. Remember, if it's axial on the left, it's got to be equatorial on the right when that flip happens, okay? And so the way you want to sort of look at it is that you can label your bonds. This bond is on top, this bond is on the bottom, this bond is on the top, this bond is on the bottom, all right? If the CH3 is on the top on the left, it's got to be on the top on the right as well, okay? So the difference between my two structures here is on the left-hand side, my methyl group is axial. And on the right-hand side, my methyl group is equatorial. All right, this molecule is going to prefer one of these conformations over the other. All right? And this goes to a new type of force. We talked about angle strain, and we talked about torsional strain. We now got another one, what's called steric strain. All right. And steric strain is pretty straightforward. The bottom line is that atoms are very claustrophobic. They want a lot of room. They don't like being crammed into a crowded environment. Okay? So steric strain is increased energy due to crowding of atoms. Okay? The lowest energy conformation is going to be when large groups have lots of space. That methyl group is a big, bulky group. All right, so let's just look. Here is my molecule on the left with my methyl group in the axial position. Here's my molecule on the right with that methyl group in the equatorial position. Which one do we think is going to be more stable? Where does the methyl group have more room? In the equatorial position or the axial position? So this one right here, it's the equatorial position is actually going to be the preferred position, right? That methyl group sticking out away from the ring. It's not crowded by all those other axial bonds, right? Axial positions are just more crowded than equatorial positions. Your neighbors are much closer. So this methyl group would much rather be sticking away from the ring where it's got a whole bunch of space to spin around and be happy, okay? So the bottom line here is the large groups are going to prefer the equatorial position. So I know that the structure on the right is more stable because large groups prefer the equatorial position.
So it's similar to like eclipsing of the other atoms again, when it's in the axiom.
Yeah, well, eclipsing was specifically for neighboring, so these ones aren't exactly neighbors, right? But they are very close, and so the idea of steric hindrance is that groups don't want to be close together.
So are we gonna have to put always draw into axial and equatorial, or is one of them gonna be implied like hydrogen in the reaction?
So you're saying you just gave me something like that?
Yeah.
That's fine. All right. It's helpful to keep track of all your bonds at first. Once you can sort of see it and you can get a little lazy, that's fine. All right, but yeah, it's just kind of helpful to make sure that you have everything drawn correctly when you're getting started. All right, so bottom line is, what are we expected to be able to do here? If I give you a bond line structure of a molecule, you need to be able to give me the chair structure of that molecule, and after it's been flipped, and look at the two and tell me which one is going to be more stable. Okay? All right, so let's do another one here. so draw me the chair structure and the flip chair here. Okay, actually before we go, is this the cis or the trans isomer of this molecule? It's a trans, right? They're pointing in opposite directions. Cool. All right, so get your chair structure drawn. See if you can fill it in, and we'll go from there. All right, so I'm going to number so I can keep track of my carbons. These two methyl groups are 1, 2, 3 carbons apart. So I'm going to call this carbon 1, this carbon 2, and this one carbon 3. Okay. For carbon 1, which direction should the axial bond be pointing, up or down? Up. What about carbon 2? Down. And what about carbon 3? Back up again. Okay, my equatorial positions are always sort of pointed away. All right. On carbon 1, I have this methyl group. I'm going to color it in blue here. that's on a wedge, so it's pointed out of the page. So I'm going to stick it on this top bond here. Okay. If on carbon 3 I color this methyl group in green here, which position should I put it in? The axial or the equatorial position? Equatorial, it's on a dashed bond now, right? So it's pointed down. All right, so before we move on here, let's try filling in these bonds again for a slightly different structure. I want to make a point here. Okay, so now we're going to fill in. Everybody, we can do this together here. Let's look up. We got these two methyl groups on carbon 1 and carbon 2. Is this the cis or the trans isomer? Cis, right? Now they're pointed in the same direction. So I'm going to put that methyl group on carbon 1. All right, it's a wedge, so it's going to go on that topmost bond. All right. But on carbon 2, if I put in that methyl group, right, it's also pointed in that same direction. So it would go on this equatorial position, not the bottom bond, because that's pointed in the opposite direction, right? So the bottom line is, just because it's a wedge doesn't mean it's axial, doesn't mean it's equatorial. You can't make it as simple as that. It's going to depend on what carbon you're talking about. So we can't just always say wedges are axial and dashes are equatorial. It doesn't work like that, right? In this case, both of these were wedged bonds. On carbon 1, it was the axial position, and on carbon 2, it was the equatorial position. Okay? So how do I know where to put it, right? Both of these are wedges. So this is pointed up, and this is pointed up. If I go to carbon 1, this is my top bond, and this is my bottom bond. All right, my topmost bond is in the axial position. But if I move to carbon 2, my topmost bond is in the equatorial position. And it's the bottom one in the axial position. All right, so again, I want to do this example specifically to make a point here. Just because it's a wedge, that does not necessarily mean that it's going to be axial. Just because it's a dash doesn't necessarily mean it's equatorial. It might be, but we got to look at those carbons specifically. All right, so that's why we got to start. That's why we started with drawing our chair structure first. If we could make it that easy, we would have started there, right? But we can't do that. All right, so going back to finish up this problem here, now we have to do our chair flip. All right, again, a very important part is keeping track of which carbon is which. If my carbon 1 is pointed up in my left chair, it's got to be pointed down in my right chair. Okay, now carbon 1 and 3 will have their axial pointed down. Okay, on carbon 1, if that methyl group was in the axial position on the left, what is it going to have to be on the right?
Equatorial.
An equatorial. And again, just sort of note, it was on the top bond, and it's still on the top bond. Okay, my green methyl group here was equatorial. So now it's going to be in the axial position. So here we have a CH3 axial. I guess I'll keep my color coding good. CH3 axial, CH3 equatorial. We flip. Now we get a CH3, the blue one in the equatorial, and the green one in the axial position. So which one of these two structures is going to be more stable? Yeah, we got one axial, one equatorial in each one, right? So in this case, they would be the same energy. So this is, again, a molecule. It's going to flip back and forth. It doesn't prefer one more than the other. They both are going to have that high energy axial position methyl group. There's nothing this molecule can do about it. So these two conformations would be the same energy. All right, but again, this is the name of the game here. Taking our bond line structure, turning it into this chair structure here, and then doing the flip so we can analyze which conformation is the lowest energy. And again, the whole logic is that big, bulky groups, they don't want to be in the axial position. Cool. All right. And we are done with Chapter 4 material. I will say that your homework for this particular thing, the bottom line is our online homework system has chair structures, but it does not grade them correctly. It does not distinguish between cis and trans isomers, which, like, what the heck are you even doing then? All right. As well as the fact that it makes it too easy to draw your chairs, and we need to practice drawing our chairs, right? So you're going to actually be submitting pencil and paper drawing of these problems as your homework, all right? The format will be that it will be a discussion forum. Once you post, you will have access to the answer key, and you'll be able to check your work that way, okay? If you are wrong on any of them, to get full credit on the assignment, you're going to have to go back and make your corrections, all right? That's how that's going to work. It would be awesome if it could be self-graded, but there's no way to kind of do it that has you practicing the drawings and to have it immediate feedback, unfortunately. All right? Cool. All right, so let's take our break and we'll get started with lab here in 15 minutes. A lot of y'all had the caffeine fairy come in the middle of the night and deliver you some samples of caffeine in your drawers. So, yeah, that was me. When you're done with your model kits, please break everything up and just stack them up here on this table.